So in my previous post, we looked at the comparison between classical mechanics and special relativity when it comes to motion of matter and light. When we're looking at propagation of matter and light at high speeds, special relativity is an important factor to consider. Now, keep in mind that motion is relative, but even though we are or we seem to be stationary while we're sitting here at our desk, we are moving very fast relative to space. Remember that the Earth is rotating at 1,000 miles per hour at the equator, and the sun is moving. So we are always moving at high speeds relative to something else. So the three things that occur at high speeds when matter and light are propagating that way at high speed is that time is dilated. So there is an increase in time, and there is a length contraction. So there is a decrease in length and there is an increase in mass. So let's take a look at time dilation. So when you're traveling at high speeds, time changes or time is perceived differently. So we'll call that the time as perceived by the person moving, and time the time of the person in motion, and T naught is the time of the observer at rest. V is the speed of the person in motion, and C is the speed of light, which is constant in a vacuum at 3 times 10 to the 8 meters per second. So what happens in time dilation? So T is going to increase in this formula. So when we look at the bottom part here, this is known as the Lorentz factor. Lorentz factor is the gamma factor, which is 1 over 1 minus v squared over c squared. It might help with calculation efficiency to calculate this Lorentz factor first, or the gamma factor, so that you'll have the value for this one here, and you'd be able to do your calculations much faster. So we can summarize this as T is equal to gamma times T naught. And that's what happens in time dilation. Second thing that occurs is length contraction. So just to clarify the time dilation before we get into the length contraction, imagine that you and your twin sister. You have a twin sister, and your twin sister is going to stay on Earth, and you will be in a spaceship that is traveling very, very fast, moving away from the planet Earth. What happens is that the time as perceived by you who are in motion is going to be different than the time perceived by your twin sister who's going to stay at rest on Earth. We can calculate the time lapsed by using this formula. So when you come back, you will see that your twin sister that stayed on Earth is actually going to appear and will actually be much older than you are. And there's a video that I posted as well in the blog about the time dilation, but this is the formula that you will use when you're looking at the time as perceived by the two different motion. This applies also to particle accelerators. When you accelerate particles, compare that to the particle that stays at rest. So it is an important thing to consider. The second thing that we look at is called the length contraction. So imagine you have a meter stick and you're standing at rest and the meter stick is flying right by you sideways at, say, close to the speed of light. When you look at this meter stick as it comes in front of you, is that it will actually appear to be shorter, to be less than 1 meter length, because it is traveling very fast. What happens with the length is that the length will decrease, and the formula L is equal to L naught times 1 minus v squared over c squared. You can also just use this form here instead of using the Lorentz or the gamma factor. This is known as the beta factor, but we're going to stick to the gamma factor here. Or L is equal to L naught over the gamma factor. So if you want to calculate the gamma factor first, then all you have to do is plug it in into our formulas here, and you don't have to calculate all these things in this pretty complicated form. The last thing that is a consequence of traveling at high speed is the mass increase. So imagine you are running, and the faster you run, the more your mass increases. So you're running faster and faster, your mass actually increases, which means that in order for you to sustain that speed so that you can go faster or at least maintain that speed when your mass is already increasing, you need to input more energy into your body so that you can maintain that same speed. So basically, as you go faster, you gain mass, and as you gain mass, you need more energy input to maintain that speed, which means you'll need a lot of energy supply to to um, to put in that speed because you're increasing your mass. So there is only a limited amount of energy that you can input, and that is the reason why we actually cannot attain the speed of light. We simply cannot go at the speed of light. So only light can go at the speed of light. What happens with mass increase is it can be calculated with this formula. M is equal to rest mass divided by 1 minus v squared over c squared square root. Or M is equal to M naught over gamma factor. So we can use this formula to look at the time dilation, length contraction, and mass increase. So let's take a look at this worksheet here in my booklet. If you have the booklet on page 22, if you try this using the formula that we have on page 22 and 23, I'd like you to try these questions first, and I will post the answers so that you can check your work.